Thank you so much for the opportunity to present this development that we have conducted at Siemens. Um, I've heard a lot of fiber Bragg grading talks here today. I just want to show you here on our typical um, turbo generator, some of these locations where we put fiber optic sensors, and most of these locations have been utilizing fiber Bragg gratings. But today I'm going to talk about a different sensing technique that does not use fiber Bragg gratings. Um, it uses white light interferometry. Um, the choice for fiber optics within our turbo generators I think, is probably the best choice. And the reason for that is you need an all dielectric material because of the extremely high electromagnetic fields that are generated inside the generator, the high voltages and the high currents, etc. And so using fiber optic sensors into our generators for Siemens energy, at least, has been since the mid 1980s. And we've progressed and used different technologies that have been developed within optical fiber sensors. And so the issue that we really have in the industry is that it has been extremely slow to adopt using optical fiber sensors, although we've been a number of decades that have utilized these sensors. And yet the industry is still very slow into adopting these as a viable commercial product. I can say that currently our most successful commercial product is the vibration monitoring that in fact, that's the one that started back in the mid 1980s using optical fibers. I think it was one of the first usages of optical fibers to monitor inside the generators. And this product we call the FOVM, fiber optic vibration monitor. We utilize this on a lot of our generators, especially the very big generators above 800 megawatts or so, and certainly on the nuclear units too. Some of these points here that we do the measurement, as you can see, most of the points are internal to the generator. That's why fiber optic sensors are ideal for that. Although there are some locations on the outside, the gussets, we instrument those with fiber Bragg gratings, multiple fiber Bragg gratings, so that we can properly adjust the weight of the generator depending on the location, the physical location of the generator, so that we can properly align the generator to avoid any imbalances when the unit is in operation. So the technology that I'm talking about today is the white light interferometry, and the way that these type of sensors are manufactured, they essentially put two reflective mirrors, as we call them, within the core of the optical fiber, and the two mirrors are separated by a known distance. And light that is propagating down the core of the optical fiber encounters the first mirror. Part of that light is reflected from that first mirror. The rest of the light is transmitted through that mirror, and then it interacts with the second mirror a distance away, and then that light is reflected off of the second mirror. And so the light from mirror number one and the light from mirror number two, they recombine at the detector, and it forms an interferogram. It forms an interference pattern. And so that is the basic construction of the sensor. And so by reading the number of fringes, so to speak, we can accurately measure the amount of stretching that Fabry-Perot etalon has undergone. And that gives us an extremely precise measurement of the strain of the substrate that the sensor is bonded to. So here we go. I'm assuming that everybody can see the presentation. On my screen, I have let me just first ask, everybody can see the left and the right side of this image that I have here. So
Yeah, we got you.
thank you. So as I mentioned, as the substrate experiences a stretching, The two reflective mirrors, they also experience the same stretching, and so the interferogram moves in position. And by counting the number of fringes, we essentially have a direct measurement of the amount of stretching that is undergone. And of course, from simple measurements of the definition of the strain, we get the amount of strain that the substrate has encountered. So I wanted to show you the location where this particular sensor has been deployed. I have here a number of photographs of this is what we call an in-field rewind. And so what we do is we remove the rotor from the generator. And then you can see here on the left-hand side, you can see we call these the teeth of the stator. And then within the teeth, we wind the generator. So we put in the physical windings, the copper windings where the current is generated from the rotation of the rotor. And so you can see for this particular generator, I believe this was an 800 megawatt generator, the diameter of the core of the stator core is roughly, it's almost 6 feet. And here on the middle picture, you can see here's a winding. Here's one winding. It takes 4 people to physically bring it into the stator so that we will wind from one end of the stator in the back to the front end of the stator here. And then we will repeat that. So we have 2 coils, a top coil and the bottom coil. What's important is that there are no cavities and there are no areas where there can be any type of discharge, electrical discharge between the coils and the stator. That could lead to catastrophic failures of the machine. And so how do you measure that? How do you monitor, how well, the coils are fit within those teeth of the stator? And so we have within the industry, we have an idea of what the tightness should be for those 2 coils. And what we wanted to do was we wanted to be able to measure the amount of tightness that those coils are under. So if you have a measurement at the beginning, whenever the generator is rewound, and then you monitor that amount of tightness as the generator progresses in its lifetime, in its age, you get an idea of whether or not you're experiencing any looseness within those coils. And in the past, this has typically done on a time basis. So it was never based on the condition of the machine. It was based on just a set period where we would have to go in there and physically measure the tightness of those coils. Bringing down a generator and removing the rotor so that you can make those measurements is very, very costly, not only to the service personnel of Siemens, but it's extremely costly to the operators of the generator. And if you have a very large generator, in this case, 800 megawatts or greater, it could be on the order of $1 million a day of lost revenue while that generator is offline. And so instead of having a time series based maintenance schedule, the idea here is, well, let's keep an online measurement of what the tightness is. And so now we have a better indication of the condition of the machine, and we can better plan for those type of outages that necessitate us going in and either retightening or rewinding the generator. And so I want to show you our own shop test that we conducted when we were first looking into the viability of this particular technology. And this is located in our Pittsburgh service center. And you can see on the right-hand side, you can see the rotor of this generator. It has been removed so we can have access to the windings and to the slots. There we call them. I was given access to 5 slots to install 5 of these sensors at various locations so we can determine their viability. I believe that this not a very big generator. This is probably a medium-sized generator here. I believe the diameter here is on the order of perhaps 1.5 meters or something like that. So here are the five slots, as we call them, that I was given access to install the sensors. I was given access to slots number 22 through 28 or 27. Yeah, there for the five sensors. What's really important in deploying any type of sensor with in any field is, yes, we want the sensor to last a very long time during the operation, but a very key critical aspect is the installation of the sensor. And in our industry, our installers are used to these very large machines that have a lot of weight associated to them. So to be gentle with the optical fiber sensors that most of us have experienced when we first use these type of sensors, it's not practical. So the sensor needs to be robust in not only in its workability during its lifetime, but also during installation. And here you can see how the installation for the shop test went about. You can see we use hammers and very stout gentlemen that are not afraid to do whatever they need to do to get the job done and finish as quickly as possible. So this is something that we keep in mind for any type of sensor that we install, or particularly the fiber optic sensors. The middle picture here shows the installation of one of the sensors. I believe it was the top sensor, the first sensor, number one, and it's you can see the black lead fiber cable that that comes from the actual sensor itself. We route these outside. This particular generator was an air-cooled generator, so there was no need for any type of pressure seal to go through a penetration. But a lot of the big generators, they are hydrogen cooled, so it's very important that not only do you have the proper sensor that can function in a hydrogen atmosphere, but also the proper components that will allow the penetration of that hydrogen barrier. And so let me just briefly talk about the benefits of this particular technology and fiber optics into our generators. So for stator winding tightness tests, they're typically conducted every 4 to 6 years, I had mentioned. With monitoring, these tests can be considered on as needed basis. So if we know the condition of the machine, we call this condition-based maintenance. If we know that an outage needs to be scheduled, material can be ordered prior to the outage and have everything ready on site, so we can minimize the amount of time it takes to bring the machine down and then bring the machine back up to operation. So of course we can postpone the normal test that we would do according to the time schedule, and perform these tests as needed. Of course, fiber optics, being an all dielectric components, are extremely important, especially measuring these measurands inside to the generator, because they're impervious to electromagnetic interferences. For this particular sensor technology, it is an absolute strain measurement, and it is not affected by temperature as your typical fiber Bragg ratings. Of course, we know the Bragg condition is twice the effective index and the pitch of the grating. So by measuring the difference in the pitch of the grating, we have a change in the Bragg condition, in the Bragg wavelength. But the effective index is something that is an order of magnitude stronger in a Bragg rating, and the effective index is a function of the temperature. So we eliminate the need to also have a temperature measurement at the sensing location, so that we can accurately measure what that absolute strain is. Of course, these fiber optic sensors are intrinsically safe, but with the white light source, we avoid using a laser source, which in our industry means that we do not have any ATEX concerns. ATEX is acronym for the atmosphere explosive, which means that if you make a penetration into a hydrogen atmosphere or any atmosphere that can be ignited, then you have to take into account what the ATEX conditions are for the amount of laser power that is being transmitted through the penetration. For white light interferometry, that is not applicable. And of course, the measurement is independent of the light intensity and any light losses in the optical train, because we're measuring the fringes. In other words, we're counting essentially the number of fringes as that interferometric pattern shifts, and so we do not have to take into account, as compared to intensity measurements, fiber optic sensors that use intensity measurements as their measure. And of course, the other big point is that interferometric measurements are very sensitive, so we can have extreme resolution in the amount of strain that is being experienced because of the interferometric aspect of the measurement. And I believe that, yes, our lawyer's company disclaimer. Thank you all for your attention.
Thank you.